Please subscribe to support the channel. Standing on the surface of our planet, gazing up at the sky, we inhabit a world that feels boundlessly vast. Earth stretches approximately 12,742 kilometers across at its equator, a sphere wrapped in oceans that cover 71% of its surface and continents that support over 8 billion human lives. When we consider the diversity packed onto this globe, from the deepest ocean trenches plunging nearly 11 kilometers below sea level to mountain peaks reaching over 8 kilometers high, from sprawling megacities housing tens of millions to remote wilderness areas untouched by human presence, our planet genuinely seems immense. We can spend entire lifetimes exploring just small fractions of Earth's surface. A person could dedicate years to understanding a single rainforest ecosystem, decades to mastering the cultural complexities of one nation, or generations to mapping the intricate cave systems beneath a single mountain range. The sheer variety of climates, ecosystems, geological formations, and human societies creates an almost overwhelming sense of planetary magnitude. Yet this feeling of vastness represents merely the beginning of a journey that will systematically dismantle our sense of scale with each progressive step outward into the cosmos. When we expand our perspective beyond Earth and examine our planetary neighbors, the first cracks appear in our geocentric sense of size. Venus, our closest planetary neighbor, measures remarkably similar to Earth with a diameter of approximately 12,000 kilometers, creating an almost twin-like comparison that initially reinforces our sense that planets exist on a comprehensible scale. Mars, the red planet that has captured human imagination for centuries, actually appears smaller than Earth, stretching only 6,792 kilometers across its equator, roughly half Earth's diameter and possessing merely 11% of Earth's mass. These comparisons might temporarily comfort us with the notion that Earth ranks respectably among the planets, but this comfort evaporates entirely when we turn our attention to the gas giants lurking in the outer solar system. Jupiter, the undisputed king of planets in our solar system, measures an absolutely staggering 139,820 kilometers in diameter. To put this in perspective that truly captures the magnitude, you could line up 11 Earths side by side across Jupiter's equator, but the real revelation comes when considering volume rather than simple diameter. Jupiter's immense size means that over 1,300 Earths could fit inside its vast bulk, with room to spare. Imagine every ocean, every continent, every mountain range, every city, and every person on Earth. Then imagine duplicating our entire planet more than 1,300 times and stuffing all these copies into Jupiter's swirling atmosphere of hydrogen and helium. Saturn, while slightly smaller than Jupiter, still dwarfs Earth with a diameter of approximately 116,000 kilometers, large enough to contain more than 760 Earths within its volume. Even the ice giants of the outer solar system, Uranus and Neptune, exceed Earth substantially, with diameters roughly 4 times larger than our own planet. The distances between these worlds add another dimension to our growing sense of cosmic scale that proves even more mind-bending than the sizes themselves. We measure interplanetary distances in astronomical units, with one astronomical unit representing the distance from Earth to the Sun, approximately 150 million kilometers. Mars, our nearest outer planetary neighbor, sits at an average distance of 1.5 astronomical units from the Sun, or about 225 million kilometers from Earth at its closest approach. This might sound like merely a larger number until we consider what it means in practical terms of travel time. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of approximately 190 kilometers per second at its fastest point, yet even at this incredible velocity, a journey to Mars would require weeks or months depending on the planetary positions. The Voyager 1 spacecraft, launched in 1977 and traveling at roughly 17 kilometers per second relative to the Sun, took over 3 years just to reach Saturn, despite Saturn being only 9.5 astronomical units from the Sun. Jupiter, at 5.2 astronomical units, sits about 778 million kilometers from the Sun at its average distance. Meaning light itself, traveling at the universe's ultimate speed limit of roughly 300,000 kilometers per second, takes over 40 minutes to make the journey from the Sun to Jupiter. When we consider that Neptune orbits at 30 astronomical units, or approximately 4.5 billion kilometers from the Sun, we begin to grasp how our solar system represents not a cozy collection of neighboring worlds but rather a vast expanse of mostly empty space with occasional planetary islands separated by oceanic gulfs of vacuum. At the center of this planetary system sits our Sun, an object so massive and energetic that it fundamentally redefines our understanding of scale. The Sun measures approximately 1.4 million kilometers in diameter, a number so large that it becomes nearly meaningless until we apply the same comparison technique we used with Jupiter. More than 100 Earths could line up side by side across the Sun's diameter, but the volumetric comparison delivers an even more stunning revelation. Over 1 million Earths could fit inside the Sun's vast sphere, with some calculations suggesting closer to 1.3 million Earths depending on how you account for packing efficiency. The Sun contains 99.86% of all the mass in our entire solar system, meaning that all the planets, moons, asteroids, comets, and every other object orbiting within the solar system combined represent barely a rounding error when compared to our star's mass. The Sun weighs approximately 2 times 10 to the 30th power kilograms, a number so enormous that it contains 33 digits when written out fully. This mass creates gravitational pull so intense that it holds every object in the solar system in its grip, keeping Earth locked in its orbit from 150 million kilometers away and maintaining Neptune's orbital path from nearly 5 billion kilometers distant. But mass and size represent only part of the Sun's extraordinary nature. At its core, temperatures reach approximately 15 million degrees Celsius, hot enough that hydrogen atoms collide with sufficient energy to overcome their electromagnetic repulsion and fuse together, creating helium and releasing tremendous amounts of energy in the process. Every second, the Sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion, and in that process, approximately 4 million tons of matter get converted directly into energy according to Einstein's famous equation. This energy radiates outward, taking thousands of years to work its way from the core to the surface through a complex journey of absorption and re-emission, before finally streaming into space as the light and heat that makes life on Earth possible. Yet for all the Sun's imposing magnitude, it represents merely an average star, a yellow dwarf of spectral type G2V that falls somewhere in the middle range of stellar sizes and masses. When we look up at the night sky and observe the stars twinkling above us, many of those distant lights actually dwarf our Sun in ways that challenge comprehension. Sirius, the brightest star in Earth's night sky and located approximately 8.6 light-years away, appears so brilliant partly because it sits relatively close to us in cosmic terms, but also because it genuinely outshines the Sun, radiating about 25 times more luminous energy than our star and measuring roughly twice its diameter. Arcturus, the brightest star in the northern celestial hemisphere and located about 37 light-years distant, appears noticeably orange-red to observers with good eyesight, a color indicating its status as an evolved giant star that has exhausted the hydrogen in its core and expanded to enormous proportions. Arcturus measures approximately 25 times larger in diameter than our Sun, meaning if you placed it where our Sun sits, its surface would extend roughly to the orbit of Mercury. If we venture further into the catalogue of stellar giants, we encounter stars that make even Arcturus seem modest. Antares, the heart of Scorpius located approximately 550 light-years away, swells to roughly 700 times the Sun's diameter, large enough that if placed at the center of our solar system, its surface would extend beyond the orbit of Mars. Betelgeuse, the red supergiant marking Orion's shoulder, varies in size but reaches dimensions approaching 1,000 times the Sun's diameter during its largest phases, potentially stretching out to encompass the orbit of Jupiter if transplanted to our solar system's center. These comparisons force us to reconsider our Sun's significance, revealing that our life-giving star represents just one of countless stellar types, either particularly large nor especially small, either remarkably bright nor notably dim. The Sun qualifies as medium-sized, middle-aged, and thoroughly unremarkable by cosmic standards, just another ordinary yellow dwarf star among hundreds of billions in our galaxy. This ordinariness actually proves fortunate for life on Earth, as the Sun's stable middle-aged character provides consistent energy output over billions of years, Unlike more massive stars that burn through their fuel supplies in mere millions of years, or smaller red dwarfs that tend toward violent flaring activity that could sterilize nearby planets. Yet this very ordinariness also begins to hint at the humbling truth that will become increasingly apparent as we expand our view further outward into space. If our Sun represents just one average star among multitudes, and if that star already dwarfs Earth by a factor of over 1 million in volume, then where does that leave our planet in the larger scheme of the cosmos? This question becomes increasingly urgent as we prepare to examine distances so vast that even our solar system's immense scale begins to seem confined and cozy by comparison. To navigate these truly cosmic distances, we need to abandon familiar units like kilometers or even astronomical units, because the numbers become unwieldy to the point of meaninglessness. Instead, astronomers use the light year, a unit that measures not time but distance, specifically the distance that light travels through the vacuum of space in one Earth year. Light moves at approximately 299,792 kilometers per second, so fast that it could circle Earth's equator more than 7 times in a single second, so fast that it reaches from Earth to the Moon in about 1.3 seconds. This incredible velocity means that light crosses the distance from the Sun to Earth, our standard astronomical unit of roughly 150 million kilometers, in approximately 8 minutes and 20 seconds. If the Sun suddenly vanished, we would continue to see it shining in the sky for over 8 additional minutes before darkness arrived, because the last light it emitted would take that long to complete its journey. When we extrapolate this incredible velocity across an entire year of continuous travel, light covers approximately 9.4 trillion kilometers, a distance so vast that it becomes the standard ruler for measuring interstellar space. This measurement proves essential because once we leave our solar system and venture out among the stars, even the distances between the nearest stellar neighbors require years for light itself to traverse, and light represents the fastest possible speed in the universe according to our current understanding of physics. Before we take that leap into interstellar space, we should properly establish where our solar system actually ends, a boundary that extends far beyond the orbits of the planets most people learn about in school. Pluto, once considered the 9th planet and now classified as a dwarf planet, orbits at an average distance of approximately 39 astronomical units from the Sun, about 5.9 billion kilometers, requiring light roughly 5.5 hours to cross that gulf. For decades, many people imagined Pluto marked the edge of the solar system, but we now understand that this represents merely the beginning of our Sun's true domain. Beyond Neptune's orbit lies the Kuiper Belt, a vast donut-shaped region of icy objects extending from about 30 astronomical units out to roughly 50 astronomical units, populated by hundreds of thousands of objects larger than 100 kilometers across and trillions of smaller bodies. These frozen remnants from the solar system's formation include dwarf planets like Pluto, Haumea, and Makemake, along with countless comets that occasionally get gravitationally perturbed and begin the long fall inward toward the Sun, eventually becoming the spectacular-tailed comets visible from Earth. But even the Kuiper Belt doesn't mark the true boundary of the Sun's gravitational influence. Far beyond this icy belt, extending from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units or more, lies the hypothetical Oort Cloud, a vast spherical shell of icy objects completely surrounding our solar system in all directions. While we have never directly observed the Oort Cloud due to the incredible distances involved and the small size of its constituent objects, scientists infer its existence from the orbital characteristics of long-period comets that occasionally plunge into the inner solar system from random directions rather than from the relatively flat plane of the planets. The Oort Cloud's outer edge, estimated at somewhere between 100,000 and 200,000 astronomical units from the Sun, marks the genuine boundary of our solar system, the region where the Sun's gravitational influence finally yields to the gravitational pull of neighboring stars. Converting these astronomical units into light travel time provides a more intuitive sense of scale. Light takes approximately 1 year to reach from the Sun to the inner edge of the Oort Cloud, and potentially 2 to 3 years to reach its outer boundary. This means our solar system, properly defined, stretches nearly 4 light-years in diameter, with the Sun at its center and this vast spherical cloud of icy objects defining its true perimeter. When people think about our solar system, they typically envision the 8 major planets contained within about 30 astronomical units, a region that light crosses in mere hours. But the reality encompasses a vastly larger volume of space where sunlight grows so dim that the sun appears as merely the brightest star in a sky full of stars, where temperatures hover mere degrees above absolute zero, and where objects orbit so slowly that a single circuit around the sun requires millions of years. This properly expansive definition of our solar system brings us finally to the threshold of interstellar space and our first encounter with another star system. The nearest star to our Sun, Proxima Centauri, lies approximately 4.24 light-years away, meaning light takes 4.24 years to travel from our Sun to this small red dwarf star. To put this distance in more tangible terms, Proxima Centauri sits roughly 268,000 astronomical units away, or about 40 trillion kilometers, a number so large that it loses all intuitive meaning. Perhaps a better way to grasp this distance involves considering travel time using actual spacecraft. The Voyager 1 probe, currently humanity's most distant spacecraft, travels at approximately 17 kilometers per second relative to the Sun and has been journeying outward since its launch in 1977. At its current speed, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it is not. The Parker Solar Probe, our fastest spacecraft at its maximum velocity of roughly 190 km per second, would still need approximately 6,700 years to cover this distance, assuming it could maintain that velocity and travel in the right direction. These time scales exceed not just individual human lifetimes, but the entire span of human civilization as we know it. The pyramids of Egypt, among humanity's most ancient monuments, were built approximately 4,500 years ago, meaning a journey to Proxima Centauri at our fastest spacecraft speeds would take longer than the entire period from ancient Egypt to the present day. Proxima Centauri actually forms part of a triple star system called Alpha Centauri, where Proxima orbits at a great distance around 2 larger stars, Alpha Centauri A and Alpha Centauri B, which orbit each other in a binary dance. This nearest stellar system to our own has captivated human imagination for decades as the obvious first target for any future interstellar mission humanity might attempt. Astronomers have discovered at least 2 planets orbiting Proxima Centauri, including one called Proxima Centauri b that sits within its star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. The prospect of a potentially habitable world orbiting our nearest stellar neighbor seems almost too convenient to be coincidence, yet even this closest possible destination for finding life beyond Earth remains utterly unreachable with current technology. The fastest interstellar probe concept currently under serious consideration, the Breakthrough Starshot Initiative, proposes using powerful laser arrays to push tiny spacecraft equipped with light sails to approximately 20% of light speed, which would allow them to reach Alpha Centauri in roughly 20 years of flight time. Even this wildly ambitious concept, which would require technological advances far beyond our current capabilities and consume enormous amounts of energy, would merely allow us to take pictures as the probes flew past at relativistic speeds, unable to slow down or stop due to the fundamental challenges of space propulsion. When we expand our view to encompass not just our nearest stellar neighbor but our local stellar neighborhood extending perhaps 30 light-years in all directions, we find ourselves contemplating a region that contains several hundred known stars, though the exact count depends on how carefully we have searched for dim red dwarfs and brown dwarfs that emit little light. Within just 10 light-years of our Sun, we find only about 14 star systems containing roughly 20 individual stars, since some of these systems feature multiple stars orbiting each other. These nearby stars include Sirius, which we mentioned earlier as the brightest star in Earth's night sky, located 8.6 light-years away, and Epsilon Eridani, a young star slightly cooler than our Sun sitting about 10.5 light-years distant. Extending our radius to 30 light-years increases the population to several hundred stars, yet even this seemingly crowded neighborhood actually consists mostly of empty space. The average distance between stars in our galactic neighborhood works out to roughly 4 to 5 light-years, meaning vast gulfs of empty vacuum separate these stellar islands. If we constructed a scale model where the Sun shrunk to the size of a basketball, Earth would be a small marble orbiting about 26 meters away, Pluto would circle at roughly 1 kilometer, the outer edge of the Oort Cloud would extend about 300 kilometers, and the nearest star, Proxima Centauri, would sit approximately 6,800 kilometers away. Roughly the flying distance from New York to Mumbai. This model reveals the profound emptiness of space, where stars represent tiny islands of matter and energy separated by oceans of vacuum so vast that light itself requires years to cross them. Our Sun and its local stellar neighborhood exist within a larger structure known as the Orion Arm, sometimes called the Orion Spur or the Orion Cygnus Arm, a minor spiral arm of the Milky Way galaxy. To understand what this means requires examining the structure of our galaxy as a whole, which reveals an architecture both elegant and immense. The Milky Way forms a barred spiral galaxy, meaning it features a central bar-shaped structure of stars with spiral arms winding outward from the ends of this bar. Astronomers currently identify 4 major spiral arms: the Perseus Arm, the Scutum Centaurus Arm, the Norma Arm, and the Sagittarius Arm, with several smaller arm segments including our own Orion Arm. These spiral arms aren't solid structures but rather regions of higher stellar density and active star formation, where dust and gas clouds accumulate and gravitational forces trigger the collapse of molecular clouds into new stars. Our solar system sits within the Orion Arm, a relatively minor structure connecting the larger Perseus and Sagittarius arms, positioned about halfway out from the galactic center to the edge of the visible disk. The Orion Arm stretches approximately 10,000 light-years in length and roughly 3,500 light-years wide, containing millions of stars including many of the brightest stars visible from Earth such as Rigel, Betelgeuse, Bellatrix, and Alnilam, all prominent members of the Orion constellation that gives this spiral arm its name. Zooming out further to view the Milky Way in its entirety reveals a galaxy of staggering proportions that dwarfs everything we have discussed so far. The Milky Way's visible disk stretches approximately 100,000 light-years in diameter, although recent measurements suggest the disk of stars might extend even further, perhaps to 170,000 light-years or more when counting the outermost stellar populations. The galactic disk maintains a relatively thin profile, roughly 1,000 light-years thick in the main disk area where our Sun resides, though this thickness increases to several thousand light-years in the central bulge region. At the very heart of the galaxy sits a supermassive black hole called Sagittarius A star, with a mass approximately 4 million times that of our Sun, around which the entire galaxy rotates. Surrounding this central black hole, a dense bulge of mostly older, yellowish stars forms an elliptical structure extending roughly 10,000 light-years from the galactic center. The spiral arms, where younger blue stars and active star-forming regions concentrate, wind outward from this central bulge through the galactic disk, creating the characteristic spiral pattern visible when we observe similar galaxies from outside. Beyond the visible disk, a vast spherical halo of globular clusters, ancient stellar populations, and mysterious dark matter extends perhaps 600,000 light-years or more from the galactic center, containing some of the oldest stars in the galaxy and serving as a vast reservoir of mass whose gravitational pull helps hold the galaxy together. The number of stars contained within this enormous structure challenges human comprehension. Conservative estimates place the stellar population at approximately 200 billion stars, while some recent studies suggest the number might reach 400 billion, or even higher when accounting for small, dim red dwarf stars that prove difficult to detect. For the sake of discussion, let us use the middle estimate of roughly 300 billion stars populating the Milky Way galaxy. This number exceeds the human capacity for intuitive understanding, but we can attempt to grasp it through comparison. If you counted 1 star per second without stopping, working 24 hours a day without rest, you would need approximately 9,500 years to count to 300 billion, longer than all of recorded human history. If every star represented $1, the galaxy would contain enough wealth to give every person currently alive on Earth roughly $37,500. Or alternatively, if every person on Earth represented 1 star, you would need approximately 37 galaxies the size of the Milky Way to equal Earth's current human population. Yet even these comparisons fail to truly capture the magnitude because they reduce stars to abstract units rather than acknowledging that each star represents an enormous ball of fusing plasma, many of them potentially hosting their own planetary systems with moons, asteroids, and perhaps even life. To traverse this galactic enormity would require time spans that make our earlier discussions of interstellar distances seem almost trivial. Light, traveling at its maximum cosmic speed, requires approximately 100,000 years to cross from one edge of the galactic disk to the other, passing through the central bulge along the way. This means that if an advanced civilization on the far side of the galaxy began beaming a message toward Earth at the speed of light around the same time that Homo sapiens first evolved in Africa, that message would just now be arriving at our solar system. Any view we have of distant regions of our galaxy shows them as they existed tens of thousands of years in the past, with the light from those regions having traveled through space for millennia before entering our telescopes. The galactic center itself, located approximately 26,000 light-years away from our solar system, appears to us as it existed 26,000 years ago, during the last ice age on Earth when woolly mammoths still roamed across frozen tundra and early humans were just beginning to develop agriculture. If astronomers in that central region were observing Earth right now with impossibly powerful telescopes, they would see our planet as it existed 26,000 years ago, completely devoid of cities, technology, or any sign of advanced civilization. Our solar system's position within this vast galactic structure provides important context for understanding our cosmic address. We orbit approximately 26,000 light-years from the galactic center, or roughly halfway between the center and the visible edge of the galactic disk, a position sometimes described as the galactic suburbs. This location proves fortunate for life in several ways. Closer to the galactic center, stars pack together much more densely, with average distances between stellar neighbors measuring less than 1 light-year rather than the 4 to 5 light-year average in our region. This crowding increases the likelihood of close stellar encounters that could gravitationally disrupt a star's planetary system, potentially flinging planets out of stable orbits or sending swarms of comets plunging into the inner system. The galactic center also experiences higher rates of supernovae, the catastrophic explosions that mark the deaths of massive stars, which release deadly radiation that could sterilize planets within dozens or even hundreds of light years. Additionally, the supermassive black hole at the galactic core, while not directly threatening to nearby stars, contributes to a generally more energetic and chaotic environment. Our position in the suburbs provides relative peace and stability, a quiet neighborhood where stars maintain respectful distances from each other and dramatic cosmic events occur rarely enough that life has time to evolve without facing constant extinction-level threats. The density variations across the galaxy reveal fascinating contrasts that further emphasize our location's character. In our region of the Orion Arm, stars typically space themselves 4 to 5 light-years apart on average, creating the relatively sparse stellar environment we discussed earlier. Moving inward toward the galactic center, this spacing decreases steadily until reaching the central bulge, where stars crowd together with average separations of less than 1 light-year, and in the very densest regions near the supermassive black hole, stars might pass within mere fractions of a light-year of each other. In such dense stellar environments, the night sky would appear dramatically different than our view from Earth, with dozens or hundreds of stars shining brightly enough to cast distinct shadows, creating a perpetually illuminated night that never experiences true darkness. Conversely, moving outward toward the edge of the galactic disk, stellar density decreases, with stars spacing themselves further and further apart until finally giving way to the vast intergalactic void. A hypothetical observer on a planet orbiting a star at the extreme edge of the galactic disk would see their own galaxy stretching across half the sky as a magnificent arc of light, while the other half remained empty except for distant galaxies appearing as faint smudges. These density gradients mean that the Milky Way experiences dramatically different stellar environments depending on location, with our solar system occupying a comfortable middle ground that is neither isolated nor overcrowded. The Milky Way doesn't sit motionless in space but rather rotates like an enormous cosmic pinwheel, with stars, gas, and dust orbiting around the galactic center under the influence of gravity. Our solar system participates in this grand rotation, traveling at approximately 220 kilometers per second relative to the galactic center, a speed that would allow us to circle Earth's equator in less than 3 minutes if we could redirect that velocity. Despite this tremendous velocity, the galactic orbit proceeds so slowly due to the immense distances involved that one complete circuit requires approximately 225 to 250 million years, a time span astronomers call a cosmic year or galactic year. The last time our solar system occupied roughly its current position in its orbit around the galaxy, dinosaurs had not yet evolved, and Earth's land masses were joined in the supercontinent Pangaea. Since the Sun formed approximately 4.6 billion years ago, it has completed roughly 18 to 20 orbits around the Milky Way, meaning our solar system has been around the galactic block fewer than 24 times in its entire existence. The dinosaurs, which dominated Earth for approximately 165 million years, existed for less than one galactic year before their extinction. All of human civilization, from the first agricultural settlements to the present day, represents a mere fraction of 1% of a single galactic orbit, an eye blink in cosmic time. Different regions of the galaxy orbit at different speeds, with inner regions completing their circuits more quickly than outer regions, though the relationship doesn't follow simple Keplerian dynamics like planetary orbits because galaxies don't concentrate their mass in a central point like our Sun does with the solar system. This differential rotation means that the spiral arm structure we see in the Milky Way and other spiral galaxies doesn't represent fixed features made of specific stars, but rather density waves that move through the galactic disk like ripples on a pond. Individual stars drift in and out of spiral arms over many millions of years, spending some time in the more crowded arm regions before moving into the less dense interarm regions, then eventually entering another spiral arm. Our solar system currently resides in the Orion Arm and will remain there for millions of years to come, but eventually, our galactic orbit will carry us into different regions with potentially different stellar densities and environmental conditions. These orbital mechanics add another layer of dynamism to our galaxy, revealing it not as a static structure frozen in space but as a constantly evolving system where matter flows, stars are born and die, and the overall architecture gradually transforms over billions of years. Now we must confront the mathematical reality of our cosmic insignificance, working through calculations that reduce our solar system to a nearly meaningless speck within the galactic whole. If the Milky Way contains approximately 300 billion stars, and our Sun represents just one of those stars, then simple division reveals that our solar system constitutes approximately 0.0000003333% of the galaxy's stellar population, or about 1/300 billionth of the total. To put this fraction in perspective, imagine the galaxy's stars represented grains of sand. A typical grain of sand measures about 0.5 millimeter in diameter, and 300 billion such grains would weigh approximately 75,000 kilograms, equivalent to a cube of sand roughly 4 meters on each side. Our solar system would represent one single grain hidden somewhere in that massive pile. Alternatively, if we consider the volume of space rather than just counting stars, our significance shrinks even further. The Milky Way's disk spans approximately 100,000 light-years in diameter and roughly 1,000 light-years thick in our region, giving it a volume of roughly 8 billion cubic light-years, though this simplifies the true shape. The Oort Cloud surrounding our solar system, which we established earlier as extending perhaps 4 light-years in diameter, creates a sphere with a volume of approximately 33 cubic light-years. This makes our solar system's volume roughly 0.000004% of the galactic disk's volume, or about 1/250 millionth of the total space. These fractions become even more humbling when we consider Earth specifically rather than our entire solar system. Earth's volume measures approximately 1 trillion cubic kilometers, while the Sun's volume reaches roughly 1.4 billion trillion cubic kilometers, meaning the Sun is about 1.3 million times larger than Earth in volume. If the galaxy contains 300 billion stars with an average size similar to our Sun, though in reality stellar sizes vary dramatically, then Earth's volume represents roughly 1/390 trillionth of the total stellar volume in the galaxy. This number is so small that it becomes essentially meaningless to human intuition. If we represented the galaxy's total stellar mass as an Olympic-sized swimming pool containing 2.5 million liters of water, Earth would be equivalent to approximately 1/10 of a single droplet, or roughly 6 microliters. Even this comparison probably overestimates Earth's significance because it considers only the stellar mass and ignores the vast quantities of dark matter, gas, dust, and other material that makes up the majority of the galaxy's total mass. When considering all matter in the galaxy, Earth's fractional contribution drops to even more infinitesimal levels, perhaps 1/10 quadrillionth or smaller, a number so tiny that it exists purely in the realm of theoretical mathematics rather than anything we can meaningfully visualize or comprehend. The implications extend beyond mere size comparisons when we consider the question of potentially habitable worlds throughout the galaxy. Recent discoveries of exoplanets, planets orbiting stars other than our Sun, have revolutionized our understanding of planetary systems commonality. The Kepler Space Telescope mission detected thousands of exoplanets by observing the tiny dimming of starlight as planets passed in front of their host stars, while other detection methods including radial velocity measurements and direct imaging have added to the catalog. Current data suggests that most stars host planetary systems, with estimates indicating that perhaps 20 to 50% of Sun-like stars might possess at least one planet in their habitable zone where liquid water could exist on the surface. If we conservatively estimate that just 5% of the Milky Way's 300 billion stars host a potentially habitable Earth-sized planet in the right orbital location with appropriate conditions for life, that suggests approximately 15 billion potentially habitable worlds might exist in our galaxy. This staggering number implies that life, even intelligent life, could be relatively common throughout the Milky Way. Yet the vast distances between stars mean that even if thousands of technological civilizations exist within our galaxy, the nearest one might still sit thousands or tens of thousands of light years away, completely isolated from us by the fundamental speed limit of the universe and the enormous gulfs of space separating stellar systems. Earth might be one habitable world among billions, each one potentially hosting its own unique biosphere, its own evolutionary history, its own story of life's emergence and development completely independent of ours. The emptiness between stars deserves particular emphasis because space truly consists almost entirely of nothing, with matter representing a rare exception rather than the rule. We have discussed average stellar distances of 4 to 5 light-years in our region of the galaxy, but what exists in those gulfs between stars? The answer is mostly vacuum, but not perfect vacuum. The interstellar medium, as astronomers call the space between stars, contains approximately 1 atom per cubic centimeter on average, though this density varies considerably with some regions nearly empty while others contain much denser molecular clouds. To appreciate how sparse this is, consider that air at Earth's surface contains approximately 30 trillion molecules per cubic centimeter, making the interstellar medium about 30 trillion times less dense than the air we breathe. The best laboratory vacuums humans can create still contain millions of particles per cubic centimeter, meaning natural space provides a vacuum far more perfect than anything we can artificially produce. Scattered through this near-perfect vacuum, we find occasional dust grains, roughly 1 per every trillion atoms, extremely thin wisps of gas, rare cosmic rays zipping through at nearly light speed, and pervasive electromagnetic radiation including visible light from stars, infrared heat, radio waves, and other forms of energy. This tenuous material, while incredibly sparse, adds up across the vast volumes of interstellar space to significant total mass, but a human floating in interstellar space would experience conditions as close to absolute nothing as the universe permits, surrounded by darkness broken only by the distant light of stars with nothing to breathe, no air pressure, and temperatures hovering just a few degrees above absolute zero. Comparing human timescales to cosmic timescales reveals another dimension of our insignificance that perhaps cuts even deeper than spatial comparisons. Our entire species, Homo sapiens, evolved approximately 300,000 years ago, a time span that feels enormous from our perspective spanning thousands of generations. Anatomically modern humans with brains and bodies essentially identical to ours have existed for roughly 200,000 years, while civilization with agriculture, writing, and cities emerged only about 10,000 years ago. Recorded history, the period for which we have written records documenting human activities, extends back roughly 5,000 years to the earliest Sumerian and Egyptian texts. The Industrial Revolution began nearly 300 years ago, and the digital age of computers and the Internet has existed for fewer than 50 years. The entire span of human civilization, from the first permanent settlements to the present day, represents roughly 0.0044% of a single galactic year, the time our solar system requires to complete one orbit around the Milky Way. All of recorded history amounts to approximately 0.00022% of a galactic year, while the Internet age represents about 0.000002%. From the galaxy's perspective, human civilization appeared mere microseconds ago, and our entire history would pass in the literal blink of an eye to any observer using galactic rotation as their clock. Extending this temporal comparison further back reveals even more humbling proportions. Our solar system formed approximately 4.6 billion years ago from a collapsing molecular cloud in a previous generation's spiral arm, meaning it has existed for roughly 20 galactic years, having made 20 complete trips around the galaxy since its birth. Earth coalesced shortly afterward, approximately 4.54 billion years ago, cooling from a molten ball of rock to a planet with a solid crust, oceans, and an atmosphere. The earliest evidence of life on Earth dates to approximately 3.8 to 4 billion years ago, when simple single-celled organisms first appeared, meaning life has existed on our planet for roughly 16 to 17 galactic years. Complex multicellular life emerged much more recently, within the last billion years or roughly 4 galactic years, while the Cambrian explosion of diverse animal life occurred approximately 540 million years ago, just over 2 galactic years in the past. The dinosaurs ruled Earth for approximately 165 million years, less than 1 galactic year, before their extinction 66 million years ago, when an asteroid impact near what is now Mexico's Yucatan Peninsula triggered a global catastrophe. Mammals then diversified and eventually gave rise to primates, which led to early hominids, which eventually evolved into our species. This entire evolutionary journey from single-celled organisms to human beings, while representing an immense span of time by human standards, amounts to merely a fraction of our solar system's existence, and an even tinier fraction of the galaxy's age. The Milky Way itself formed approximately 13.6 billion years ago, within a few hundred million years after the Big Bang that initiated our universe, meaning our galaxy has existed for roughly 3 times longer than our solar system and approximately 60 times longer than our species. From this perspective, humanity represents not just a spatial speck but also a temporal flash, a brief moment of consciousness that emerged very recently in cosmic terms and whose future duration remains entirely uncertain. Our achievements in space exploration, while remarkable from a human perspective, underscore rather than diminish our cosmic insignificance when measured against galactic scales. Humanity's first steps beyond Earth began in 1957 with the launch of Sputnik 1, the Soviet satellite that inaugurated the space age, followed by Yuri Gagarin's orbit of Earth in 1961 as the first human in space, and Neil Armstrong and Buzz Aldrin's historic first steps on the Moon in 1969 during the Apollo 11 mission. These achievements represented extraordinary technical accomplishments and demonstrated that humans could venture beyond our home planet. But the Moon orbits merely 384,000 kilometers from Earth, a distance that light crosses in 1.3 seconds. The Apollo astronauts traveled further from Earth than any humans before or since, yet they never left our planet's immediate neighborhood, remaining well within the Earth-Moon system and never approaching even the nearest planet. Robotic probes have ventured much further, with the Voyager missions representing our most distant emissaries to the cosmos. Voyager 1, launched in September 1977, passed through the outer solar system, sending back stunning images of Jupiter, Saturn, and their moons before heading into interstellar space. In August 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind from our Sun gives way to the interstellar medium, officially becoming the first human-made object to enter interstellar space. As of now in late 2025, Voyager 1 travels approximately 24 billion kilometers from Earth, or about 161 astronomical units, having journeyed for nearly 48 years to reach this distance. This achievement, while extraordinary, must be placed in proper cosmic context. Voyager 1 has barely left our solar system if we define the system's boundary as the outer edge of the Oort Cloud, which extends perhaps 100,000 astronomical units, or more from the Sun. The probe has covered approximately 0.16% of the distance to that outer boundary after nearly 5 decades of continuous travel. At its current speed of about 17 kilometers per second, Voyager 1 would require approximately 300 years to reach the inner edge of the Oort Cloud and potentially 15,000 to 30,000 years to completely traverse it and emerge into true interstellar space beyond the Sun's gravitational domain. Even then, the probe would still need approximately 73,000 additional years to reach Proxima Centauri, our nearest stellar neighbor, assuming it were headed in that direction. In reality, Voyager 1 travels toward the constellation Ophiuchus and will pass within roughly 1.6 light-years of the star Gliese 445 in approximately 40,000 years, though by that time the spacecraft's power supply will have been exhausted for tens of thousands of years and it will coast silently through space as an inert artifact of a civilization that may or may not still exist. Voyager 2, following a different trajectory, will pass within 1.7 light-years of the star Ross 248 in about 40,000 years before continuing its lonely journey into the galactic depths. These probes, along with Pioneer 10 and Pioneer 11, which also head outward on escape trajectories from the solar system, represent humanity's first tentative reach beyond our solar system, yet they move so slowly relative to galactic distances that they will likely drift through space for billions of years without ever approaching another star closely. More recent missions have pushed the boundaries of solar system exploration further, with the New Horizons spacecraft flying past Pluto in July 2015 and revealing that distant world in unprecedented detail, showing a geologically active surface with nitrogen ice plains, water ice mountains, and a complex atmosphere despite temperatures hundreds of degrees below freezing. New Horizons then continued into the Kuiper Belt, flying past the contact binary object Arrokoth in January 2019 and sending back data about this pristine remnant from the solar system's formation. The spacecraft continues outward and will eventually join the Voyagers in interstellar space, though it too will take tens of thousands of years to reach even the nearest stars. Closer to home, we have achieved remarkable successes studying Mars with multiple rovers including Curiosity and Perseverance, orbiting and landing probes at Venus, exploring asteroids with sample return missions, and even landing on a comet with the Rosetta mission's Philae lander. Yet all of these accomplishments occur within the tiny bubble of our immediate solar system, the inner few astronomical units where planets orbit, and where spacecraft can reach destinations in months or years rather than decades or centuries. The outer solar system remains largely unexplored, with only brief flybys of the giant planets and their moons, while the vast volume of the Kuiper Belt and the theoretical Oort Cloud have barely been studied. The interstellar space beyond, containing hundreds of billions of stars and potentially trillions of planets, remains utterly beyond our reach with current or foreseeable technology. The challenges of interstellar travel reveal fundamental limitations that suggest humanity may never directly explore even a tiny fraction of our galaxy. At conventional rocket speeds, ranging from a few dozen to perhaps a few hundred kilometers per second at best, journeys to even the nearest stars require thousands or tens of thousands of years, time frames that exceed the entire span of human civilization. Any interstellar mission using current propulsion technology would need to function as a generation ship, with multiple successive generations of crew members living and dying during the voyage, raising profound questions about whether the descendants of the original crew would or should be obligated to complete a mission they never chose to undertake. Alternatively, we might imagine putting crew into some form of suspended animation or hibernation, though no such technology currently exists, and the biological challenges of keeping humans viable for millennia remain daunting if not impossible. The energy requirements alone stagger the imagination. Accelerating even a small spacecraft to 10% of light speed, which would allow a journey to Proxima Centauri in roughly 42 years, would require energy equivalent to billions of tons of chemical fuel or years of output from a nuclear reactor, assuming perfect conversion efficiency. Slowing down upon arrival would require an equal amount of energy, doubling the total energy budget. These energy requirements scale with the square of velocity, meaning that reaching 20% of light speed would require 4 times as much energy as 10%, and reaching 50% would require 25 times as much, quickly making higher speeds impossibly energy-intensive even if we could somehow achieve them. Various theoretical propulsion concepts have been proposed to address these challenges, ranging from nuclear pulse propulsion using atomic bomb explosions to accelerate spacecraft, to antimatter rockets that would harness the perfect mass-energy conversion of matter-antimatter annihilation, to laser sail concepts like breakthrough starshot that would use powerful laser arrays to push lightweight probes equipped with reflective sails. Each concept faces enormous technical challenges and most remain purely theoretical with no clear path to practical implementation. Even if we somehow solved the propulsion problem and could send robotic probes or crewed missions to nearby stars, the distances involved create another fundamental barrier: communication delay. A probe orbiting Proxima Centauri would receive our commands 4.24 years after we sent them, and would take another 4.24 years to send its response, creating a round-trip communication time of 8.5 years. This delay makes real-time control impossible and means that mission controllers would need to plan activities many years in advance, with any problems or unexpected situations requiring years for information to reach Earth and further years for new instructions to arrive at the spacecraft. A mission to a star 30 light-years away would face 60-year round-trip communication delays, meaning engineers who designed and launched the mission would likely be retired or deceased before receiving confirmation that the spacecraft successfully arrived. These fundamental limitations imposed by the finite speed of light suggest that even if humanity survives for millions of years and develops technologies far beyond our current capabilities, we may remain forever confined to exploring only our immediate stellar neighborhood, while the vast majority of the galaxy remains forever beyond our direct reach. The great silence of the cosmos, sometimes called the Fermi paradox after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" adds another layer to our contemplation of cosmic insignificance. If potentially habitable planets number in the billions throughout our galaxy, and if life arises relatively easily when conditions permit, and if some fraction of life eventually develops intelligence and technology, then why do we see no evidence of other civilizations? Why have we detected no radio signals from alien broadcasts, no evidence of massive engineering projects that would be visible across interstellar distances? No signs that any species has colonized the galaxy in the way that some futurists imagine humanity might? The absence of contact despite decades of searching through programs like SETI, the search for extraterrestrial intelligence, suggests several possible explanations, none of them particularly comforting. Perhaps life is extraordinarily rare despite the abundance of potentially habitable planets, making Earth a precious anomaly rather than a typical example. Perhaps intelligence is rare even when simple life exists, suggesting that the leap from single-celled organisms to complex multicellular life and eventually to technological civilization involves improbable steps that rarely occur. Perhaps civilizations invariably destroy themselves shortly after developing technology, whether through nuclear war, environmental catastrophe, pandemics, or other existential threats, meaning the galaxy might be filled with dead civilizations that briefly flickered into existence before extinguishing. Perhaps the distances are simply too vast and the energy requirements too great for any civilization to meaningfully explore or communicate across the galaxy, leaving each technological species isolated on their world or confined to their immediate stellar neighborhood, forever unable to bridge the cosmic gulfs to contact others. Or perhaps intelligence and technology represent evolutionary dead ends that ultimately reduce a species' survival prospects rather than enhancing them, explaining why simple life might be common throughout the galaxy while technological civilizations remain vanishingly rare. Each of these possible explanations carries profound implications for humanity's significance. If life is extraordinarily rare, then Earth becomes precious beyond measure, possibly the only world in our galaxy or even our cosmic horizon where the universe became aware of itself, where matter organized into complex forms capable of contemplating their own existence and the nature of reality. This scenario would grant humanity enormous cosmic importance despite our tiny spatial scale, making us stewards of consciousness in an otherwise dead universe. Conversely, if technological civilizations commonly self-destruct, then our current moment represents a critical period where humanity must navigate existential risks carefully or join the countless failed species that came before us, our significance measured only by whether we manage to survive our technological adolescence. If civilizations simply remain isolated by the vastness of space, then our insignificance becomes even more profound, with billions of worlds potentially hosting intelligent life but each one forever alone, separated by gulfs too vast to meaningfully bridge, making the galaxy a cosmic archipelago of isolated consciousness rather than the connected community that science fiction has long imagined. The resolution to the Fermi paradox remains unknown, but any answer will fundamentally inform our understanding of humanity's place in the cosmos and whether our existence represents something remarkable and rare or merely one example among countless others of the universe's tendency to generate complex, self-aware structures. The perspective we have developed throughout this exploration, moving from Earth through the solar system to the stellar neighborhood and finally to our position within the Milky Way as a whole, forces a profound reckoning with our cosmic status. We are inhabitants of a medium-sized rocky planet orbiting an unremarkable yellow dwarf star located in a minor spiral arm roughly halfway out from the center of a large spiral galaxy that contains hundreds of billions of similar or more impressive stars. Our planet represents one among potentially billions of habitable worlds in the galaxy, while our star represents merely one among hundreds of billions, and our galaxy itself represents just one among hundreds of billions or perhaps trillions of galaxies scattered throughout the observable universe, though that cosmic scale extends beyond our current discussion. By every quantitative measure, whether considering size, mass, energy output, or longevity, humanity registers as cosmically insignificant, a brief flash of consciousness on a tiny world orbiting a common star in an unremarkable location within a large but not exceptional galaxy. Our entire history, from the first stone tools chipped by ancestral hominids to the most advanced spacecraft and particle accelerators of the modern era, spans less time than it takes our solar system to complete one orbit around the galactic center. Our species' lifespan, even if we survive for millions of years into the future, will likely represent a tiny fraction of the galaxy's total existence. The space we occupy amounts to less than a droplet in an ocean, while the matter we comprise barely registers even when measured with the most sensitive instruments. Yet this cosmic insignificance coexists with a remarkable and paradoxical fact. Despite our tiny scale and brief existence, humanity has managed to comprehend and measure these vast cosmic distances and timescales that dwarf us so completely. We have developed mathematics sophisticated enough to calculate our motion through space and time with extraordinary precision. We have built instruments that can detect photons that have traveled for thousands or millions of years across the galaxy to reach our telescopes. We have decoded the physical laws governing stellar evolution, galactic dynamics, and the fundamental forces that shape the universe at every scale. We have sent robotic ambassadors beyond our solar system carrying messages for any hypothetical aliens who might encounter them millions of years hence. We have looked back through time by observing distant objects whose light shows them as they existed when that light began its journey toward Earth, effectively creating telescopes that function as time machines peering into the ancient past. Our minds, products of billions of years of evolution on this insignificant speck of rock, have somehow developed the capacity to contemplate the vastness that contains us and to feel wonder, awe, and even a strange kind of existential vertigo when confronting the scale of the cosmos. This ability to comprehend our own insignificance represents something genuinely remarkable, perhaps even unique in our galaxy if life and especially intelligent life proves sufficiently rare. The universe, through us, has developed the capacity to know itself, to measure itself, to understand its own physical laws and evolutionary history. The atoms that make up our bodies were forged in the cores of stars that lived and died billions of years ago, dispersing their enriched material into space where it eventually coalesced into new stellar systems, including our own. We are, quite literally, made of star stuff, composed of elements created through nuclear fusion in stellar cores and scattered through space by supernovae explosions. Every carbon atom in our bodies, every oxygen molecule we breathe, every calcium atom in our bones, Every iron atom in our blood once resided in the interior of a star that may have existed long before our solar system formed. In this sense, we represent the universe examining itself, consciousness emerging from matter through the long, slow processes of stellar evolution, planet formation, and biological evolution, eventually giving rise to beings capable of measuring cosmic distances, calculating galactic rotation curves, and feeling awe at the immensity of space and time. The emotional and philosophical response to this cosmic perspective varies dramatically among individuals and cultures. Some find the vastness of the galaxy and our tiny place within it profoundly depressing, experiencing an existential crisis when confronting the scale of space and time that reduces human affairs to apparent meaninglessness. If nothing we do matters on a cosmic scale, if our planet represents an insignificant speck in our species' a brief flicker, then why should any of our concerns, achievements, or struggles hold meaning? This nihilistic response to cosmic scale has troubled philosophers and thoughtful individuals for centuries, intensifying as our understanding of the universe's true size has grown. Others find the same perspective liberating rather than depressing, reasoning that if nothing matters cosmically, then we are free to create our own meaning and purpose without the pressure of cosmic significance, allowed to simply exist and experience without requiring validation from the universe. Still others find the vastness inspiring rather than disturbing, feeling wonder and excitement at being part of something so immense and ancient, privileged to exist in a universe capable of generating consciousness and beauty despite its overwhelming scale. The fact that we can comprehend our insignificance becomes, in this view, a kind of significance in itself, transforming what might seem like cosmic loneliness into cosmic connection. Scientific understanding of our galactic context continues to evolve and deepen as new observations and theoretical insights refine our picture of the Milky Way and our place within it. Recent measurements using the Gaia Space Telescope, which has precisely measured the positions and motions of over 1 billion stars, have revolutionized our understanding of galactic structure and dynamics, revealing that the Milky Way has a more complex history than previously suspected, including evidence of past collisions and mergers with smaller galaxies that left their mark on stellar populations and kinematics. Studies of dark matter, the mysterious invisible substance that appears to comprise the majority of the galaxy's mass, continue to probe the nature of this unknown component that helps hold galaxies together through gravitational attraction despite emitting no light. Exoplanet surveys continue to discover thousands of new worlds orbiting other stars, refining our estimates of how common different types of planets are throughout the galaxy and improving our understanding of where habitable conditions might exist. Observations of star formation regions using infrared and radio telescopes reveal the processes by which new stellar systems emerge from collapsing molecular clouds, while studies of stellar populations in different regions help astronomers understand the galaxy's evolutionary history and chemical enrichment over billions of years. Looking to the future, our understanding of the Milky Way will continue to improve as technology advances and new observational capabilities come online. The James Webb Space Telescope, launched in December 2021, provides unprecedented infrared vision that can peer through dust clouds and study the earliest stages of star and planet formation in exquisite detail. Future extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope when completed, will provide ground-based observations with unprecedented resolution and sensitivity, potentially allowing direct imaging of Earth-sized exoplanets around nearby stars and detailed studies of stellar populations throughout the galaxy. Radio telescope arrays continue to expand and improve, with facilities like the Square Kilometer Array promising revolutionary capabilities for studying the cold hydrogen gas that traces galactic structure and feeds star formation. Astrometry missions building on Gaia's success will measure stellar positions and motions with even greater precision, mapping the galaxy's architecture and dynamics in 3 dimensions and revealing subtle structures that current observations cannot detect. Each advance in observational capability brings new surprises and discoveries, reminding us that despite centuries of astronomical study, we still have much to learn about the galaxy that contains us. The question of whether humanity will ever directly explore more than a tiny fraction of the Milky Way remains open, dependent on technological advances we cannot currently predict and on whether our civilization survives long enough to develop capabilities that seem impossible today. Historical precedent suggests caution about declaring anything permanently impossible. Medieval scholars would have found the idea of humans walking on the moon absurd. Early 20th century scientists believed space travel impossible before the development of rocket technology proved them wrong, and physicists in the early 1900s could not have imagined the technologies we now take for granted like computers, lasers, and nuclear power. Perhaps future breakthroughs in physics will reveal new principles that allow circumventing or manipulating the speed of light limit, making interstellar travel practical in ways we cannot currently conceive. Perhaps advances in artificial intelligence and robotics will enable self-replicating probes that could gradually spread throughout the galaxy over millions of years, exploring and reporting back even if biological humans never leave the solar system. Perhaps some form of consciousness uploading or digital existence will allow humans to escape biological limitations and transfer between stars as information streams, existing as software rather than flesh. Or perhaps none of these possibilities will materialize and humanity will remain forever confined to our solar system or immediate stellar neighborhood, making the vast majority of the galaxy eternally beyond our direct reach regardless of how long we survive. Regardless of whether we ever physically explore the galaxy, the project of understanding our cosmic context through observation and theory continues to reveal profound truths about the universe and our place within it. Every measurement of a stellar distance, every observation of an exoplanet, every calculation of galactic rotation contributes to a comprehensive picture of the Milky Way as a vast, ancient, and complex system governed by physical laws we increasingly comprehend. This understanding itself represents an extraordinary achievement, demonstrating that intelligence and curiosity can overcome the limitations of size, lifespan, and location to grasp cosmic truths that dwarf the individual mind contemplating them. When we look up at the night sky and see the Milky Way stretching as a luminous band across the darkness, we are seeing our galaxy from inside, viewing billions of distant stars whose combined light creates that misty glow that ancient cultures imagined as spilled milk or a river of souls. Modern astronomy allows us to understand what we see in ways that transform casual stargazing into a profound connection with cosmic reality, knowing that we view a structure 100,000 light-years across containing hundreds of billions of stars, many with their own planetary systems, all rotating in a grand spiral around a central supermassive black hole. Our own solar system occupying an unremarkable location in this immense architecture. The full circle of this exploration brings us back to Earth with a transformed perspective. We began by considering our planet as it appears to us in daily experience, a vast world of diverse environments and teeming life, and we have journeyed outward through expanding spheres of cosmic context that progressively reduced Earth's apparent significance. Yet, having completed this journey and confronted our cosmic smallness directly, we return to Earth not with despair but with a deeper appreciation for both our insignificance and our significance. Yes, we are tiny. Yes, we are brief. Yes, we occupy an unremarkable location in an incomprehensibly vast galaxy. But we are also conscious, capable of wonder, able to comprehend and measure the very vastness that dwarfs us. We are the universe examining itself, matter organized in such a way that it can contemplate its own existence and nature. Our smallness in space and time does not negate the internal richness of human experience, the beauty we create and perceive, the love we feel for each other, the curiosity that drives us to explore and understand, or the meaning we find in our brief existence. The galaxy's vastness makes each human life cosmically insignificant in one sense, but the rarity or uniqueness of consciousness might make each awareness infinitely precious in another sense, creating a paradox where we are simultaneously meaningless and meaningful depending on the framework we choose for evaluation. This paradox suggests that cosmic significance operates on multiple levels simultaneously. On the scale of space and time and energy, humanity barely registers, our planet a speck, our civilization a flicker, our achievements invisible beyond our immediate stellar neighborhood. On the scale of complexity and consciousness, however, human minds might represent some of the most intricate and remarkable structures in the entire galaxy, complex beyond measure despite occupying mere kilograms of mass and existing for mere decades. A single human brain contains approximately 86 billion neurons, each connected to thousands of others through trillions of synapses, creating a network of staggering complexity that gives rise to consciousness, memory, emotion, creativity, and reason. This biological computer, evolved over billions of years and assembled according to genetic instructions refined by natural selection, processes information and generates subjective experience in ways we still barely understand despite decades of neuroscience research. The fact that such complexity can emerge from matter through purely natural processes represents something genuinely extraordinary, arguably more remarkable than the vast distances and enormous energies that characterize galactic space. Perhaps significance should be measured not by spatial extent or temporal duration but by complexity and consciousness, in which case humanity might represent a peak rather than a footnote in cosmic evolution. The ongoing scientific study of our galaxy and our place within it continues to generate new questions even as it answers old ones. How many technological civilizations currently exist in the Milky Way? And if the number is non-zero, why have we detected no evidence of them? What is the nature of dark matter that comprises most of the galaxy's mass? And will we ever detect it directly or understand its properties? How did the Milky Way form and evolve over its 13+ billion-year history? And what collisions and mergers shaped its current structure? How many potentially habitable planets exist within a few thousand light-years of Earth? And how might we search them for signs of life? What role do supermassive black holes play in galaxy evolution? And how did the 4 million solar mass black hole at our galactic center form and grow? How will the Milky Way evolve in the future? And what will happen when it collides with the Andromeda Galaxy in approximately 4 billion years? Each question opens new avenues of investigation and each answer typically generates additional questions, ensuring that galactic astronomy will remain an active and exciting field of study for generations to come. For those of us living in this particular moment of cosmic history, approximately 13.8 billion years after the Big Bang, 4.6 billion years after the Sun's formation, 3.8 billion years after life emerged on Earth, and 300,000 years after the evolution of our species, the perspective we gain from understanding our galactic context offers both humility and wonder. Humility because we now know with certainty that we inhabit no privileged position in space or time, that our planet circles an ordinary star in an ordinary location within an ordinary galaxy among billions of galaxies in the observable universe, and that nothing about our cosmic address suggests any special significance or central importance. Wonder because despite this cosmic ordinariness, we exist at all, conscious beings capable of joy and suffering, creativity and discovery, love and loss, meaning and purpose, able to contemplate the universe that contains us and to measure the very scales that reduce us to insignificance. The universe is vastly larger than us, but we are complex enough to comprehend that vastness. The galaxy existed for billions of years before us and will persist for billions of years after us, but we are here now, experiencing this moment, aware and alive and curious. Ultimately, the realization of how small we are in the Milky Way need not lead to nihilism or despair, but rather to a sense of cosmic perspective that enriches rather than diminishes human experience. Knowing our true scale relative to the galaxy and the universe beyond doesn't make our daily concerns meaningless, but rather contextualizes them within a larger framework that can be simultaneously humbling and liberating. The problems we face as individuals, societies, and as a species remain real and important regardless of cosmic scale. Our struggles to find meaning, build just societies, protect our environment, expand our knowledge, create beauty, reduce suffering, and flourish during our brief time of awareness all remain worthwhile regardless of whether they register on galactic scales. If anything, the recognition of our smallness and rarity might enhance our appreciation for existence itself, making us more conscious of how precious and improbable our situation is and how important it is to make the most of the brief time we have as conscious beings in this vast cosmos. Standing again on Earth's surface after our imaginative journey through the scales of the Milky Way, we can look up at the night sky with transformed vision. Those points of light scattered across the darkness are not mere decorations but rather distant suns like our own, many hosting their own planets, each one separated from us by gulfs of space requiring years or centuries or millennia for light to traverse. The misty band of the Milky Way stretching across the darkest skies represents our view of the galactic disk from within, billions of stars too distant to resolve individually but collectively creating a luminous fog. Every direction we look shows us the past, with light from nearby stars showing them as they existed years ago and light from distant stars showing them as they existed centuries or millennia ago. We are embedded within a structure so vast that light requires 100,000 years to cross it, yet so finely tuned that it has permitted the emergence of stable solar systems, rocky planets, liquid water, chemical evolution, biological life, and eventually conscious beings capable of contemplating their own cosmic insignificance. You won't believe how small we are in the Milky Way, not because the mathematics is incomprehensible or the scales unimaginable, though both are certainly challenging, but because human psychology naturally resists this level of diminishment, our evolved cognition preferring to place ourselves at the center of importance even when evidence overwhelmingly demonstrates otherwise. Yet accepting this smallness doesn't require abandoning meaning or succumbing to existential despair, but rather cultivating a more mature and realistic understanding of our situation. We are small, yes, perhaps incomprehensibly small when measured against galactic standards. We are brief, yes, existing for an eye blink in cosmic time. But we are also conscious, capable of grasping these truths that our size and duration would seem to preclude us from understanding. That consciousness, that capacity for wonder and comprehension, represents something genuinely remarkable regardless of the spatial and temporal scales involved. In measuring the galaxy and recognizing our smallness within it, we demonstrate a kind of greatness that transcends simple metrics of size, duration, or energy. We are small but aware, brief but curious, insignificant but capable of comprehending that insignificance, and finding meaning nonetheless. That paradoxical combination defines the human condition in our cosmic context, forever tiny yet reaching toward understanding, forever ephemeral yet yearning for permanence, forever insignificant yet creating significance through the simple fact of our awareness and our wonder at the vast, ancient, magnificent galaxy that contains us. The contemplation of our cosmic smallness inevitably leads us to consider what lessons or practical implications might flow from this knowledge. Throughout human history, our understanding of our place in the cosmos has profoundly influenced philosophy, culture, and even thought. When ancient civilizations believed Earth sat at the center of creation with the heavens revolving around us, this geocentric model reinforced notions of human importance and divine attention focused specifically on our world and our actions. The Copernican revolution, which displaced Earth from the center of the solar system and revealed we orbit the Sun rather than vice versa, triggered not just a scientific transformation but a philosophical crisis that took centuries to fully process. If Earth doesn't occupy the center, does that mean humanity lacks the special status we assumed? The subsequent discoveries that our Sun represents merely one star among multitudes, that our galaxy contains billions of such stars, and that the universe contains billions of galaxies have continued this process of cosmic demotion, each revelation forcing another adjustment in how we conceive our significance and purpose. Some thinkers have argued that this progressive cosmic demotion should fundamentally alter human behavior and priorities. If we occupy no special place in the universe, if consciousness and intelligence might be common throughout the galaxy, and if nothing we do registers on cosmic scales, then perhaps we should abandon grandiose notions of destiny or purpose and focus instead on reducing suffering and increasing well-being during our brief existence. This perspective, sometimes called cosmic humanism or cosmic existentialism, suggests that meaning must be constructed by humans for humans rather than discovered in some objective cosmic plan, because no such plan exists and the universe remains fundamentally indifferent to our existence or extinction. Other thinkers reach nearly opposite conclusions from the same cosmic facts, arguing that if we represent rare or unique instances of consciousness in a vast unconscious universe, then we bear enormous responsibility to preserve and expand that consciousness, making our choices deeply meaningful precisely because consciousness might be precious and fragile on cosmic scales. Still others maintain that cosmic scale provides no guidance whatsoever for human ethics or meaning, that questions of how we should live and what matters must be answered on human scales using human reasoning rather than by reference to galactic dimensions or timescales that have no direct bearing on daily life. The psychological impact of cosmic perspective varies tremendously between individuals based on temperament, cultural background, philosophical beliefs, and personal circumstances. Some people report experiencing what has been called the overview effect, a cognitive shift in awareness that results from viewing Earth from space or contemplating cosmic scales, characterized by overwhelming emotion, a sense of unity with all life, and a recognition of the fragility and preciousness of our planetary home. Astronauts who have seen Earth from orbit frequently describe this experience, reporting that viewing our planet as a small blue sphere suspended in the darkness of space, with no visible borders between nations and all of humanity sharing one fragile atmosphere, fundamentally altered their sense of identity and priority. They describe Earth looking impossibly delicate and beautiful against the harsh void of space, the thin layer of atmosphere appearing as a gossamer veil protecting the only life we know exists anywhere in the universe. This perspective often generates what researchers call the universalist orientation, a tendency to identify with humanity as a whole rather than particular nations or groups, an increased concern for environmental protection and peaceful cooperation, since from space the conflicts and divisions that dominate human affairs appear trivial compared to our shared fate as inhabitants of one small world. Other individuals respond to cosmic scale with anxiety or existential dread, experiencing what might be called cosmic horror when confronting the true vastness of space and time. This reaction appears throughout literature and philosophy, perhaps most famously in the writings of H.P. Lovecraft, whose cosmic horror stories emphasized human insignificance in the face of incomprehensible cosmic entities and scales, arguing that true understanding of our place in the universe would drive humans mad with terror at our meaninglessness. While Lovecraft's fiction dramatized this response to extremes, the underlying anxiety about cosmic insignificance represents a genuine psychological reaction some people experience when contemplating galactic or universal scales. The infinite spaces frightened philosopher Blaise Pascal in the 17th century, centuries before modern astronomy revealed the true extent of those spaces, and similar sentiments appear throughout existentialist philosophy in the 19th and 20th centuries as thinkers grappled with the apparent meaninglessness of human existence in an indifferent universe. The vastness of the galaxy can trigger feelings of loneliness, isolation, or nihilistic despair in those predisposed to such reactions, particularly if they previously found meaning in beliefs about human centrality or cosmic purpose that scientific knowledge has undermined. Yet many people integrate knowledge of cosmic scale into their worldview without experiencing either the transcendent unity of the overview effect or the existential dread of cosmic horror, instead simply accepting our galactic context as an interesting fact about reality that informs their understanding without dramatically altering their emotional life or sense of meaning. This pragmatic acceptance might actually represent the most common response, with most people acknowledging intellectually that Earth orbits an ordinary star in an ordinary location within a vast galaxy while continuing to find meaning and purpose in relationships, work, creativity, community, and the immediate concerns of daily life. The fact that our solar system represents one among hundreds of billions doesn't prevent people from loving their children, pursuing their goals, creating art, seeking knowledge, or working to improve society, suggesting that meaning operates independently of cosmic scale for most practical purposes. A beautiful sunset doesn't become less beautiful because we know the sun represents merely one star among multitudes. A piece of music doesn't lose its emotional power because the composer lived on a speck orbiting an unremarkable star, and human relationships don't become less meaningful because they occur on a tiny planet in a vast galaxy. This resilience of human meaning in the face of cosmic insignificance suggests something important about how consciousness generates value and significance. Meaning appears to be inherently subjective and relational, arising from the interactions between conscious beings and between consciousness and the world, rather than being an objective property stamped onto things by cosmic importance. A galaxy spanning 100,000 light-years and containing hundreds of billions of stars might be physically larger than a human being by incomprehensible factors, but size doesn't determine meaning or value in any straightforward way. A human mind experiencing love or wonder or creativity might be more meaningful in relevant senses than the vast empty space between stars, even though that empty space occupies incomparably more volume. The question of what matters and what has value depends fundamentally on the perspective from which we ask the question, and conscious beings represent the only perspective from which such questions make sense. The galaxy doesn't care about its own size or age, lacks any awareness of containing billions of stars, and experiences nothing whatsoever regarding its own existence. Only conscious beings can care about anything, find anything meaningful, or experience existence at all, which suggests that consciousness represents the locus of value and significance regardless of physical scale. This perspective helps resolve the apparent paradox of simultaneous cosmic insignificance and experiential significance. We are physically tiny and temporally brief when measured against galactic scales, but physical size and duration don't exhaust what matters about existence. The richness of conscious experience, the depth of understanding, the complexity of thought and emotion, the capacity for creativity and compassion and curiosity all represent dimensions of significance that operate independently of spatial extent or temporal duration. A human lifetime of 80 years might be an eye blink in galactic time, but within that eye blink an individual can experience tremendous joy and suffering, can love and be loved, can create beauty and discover truth, can help others and contribute to the flourishing of their community, can experience wonder at the cosmos and satisfaction in understanding. These experiences and achievements matter to the individuals who experience them and to the communities they affect, creating a sphere of significance that doesn't require cosmic scale to be genuine and valuable. The fact that none of this registers on galactic scales becomes irrelevant when we recognize that the question of what matters must be answered from within conscious experience rather than from some imaginary external cosmic perspective. The scientific worldview that reveals our cosmic smallness also reveals the remarkable journey that led to our existence, a 4-billion-year evolutionary epoch on Earth preceded by billions of years of cosmic evolution that set the stage for life's emergence. Understanding this deep history provides another dimension of perspective on our situation that enriches rather than diminishes the wonder of existence. The atoms comprising our bodies didn't always exist but were forged through nuclear fusion in the hearts of stars that lived and died long before our solar system formed. Hydrogen, the simplest element created in the Big Bang itself, fused into helium in stellar cores through the same process that powers our Sun today. As stars exhausted their hydrogen fuel and evolved into red giants, helium fusion created carbon and oxygen, the fundamental building blocks of organic chemistry. The heaviest elements, including iron, were created in the cores of massive stars through successive fusion reactions, each producing heavier elements until reaching iron, where fusion no longer releases energy. Elements heavier than iron, including the gold in jewelry and the uranium in nuclear reactors, formed through rapid neutron capture during supernova explosions when massive stars reached the end of their lives and collapsed catastrophically before rebounding in explosions that briefly outshone entire galaxies. These violent stellar deaths scattered enriched material into the interstellar medium, seeding space with heavy elements that could eventually form rocky planets and provide the raw materials for life. Our solar system coalesced approximately 4.6 billion years ago from a molecular cloud that contained material from multiple previous generations of stars, giving Earth and the other terrestrial planets the silicon, iron, oxygen, carbon, and other heavy elements needed for their composition. Without those ancient supernovae enriching the galaxy with heavy elements, planets like Earth couldn't exist and life as we know it couldn't emerge. We are genuinely children of the stars in the most literal sense, composed of matter that cycled through stellar cores and supernova explosions before eventually assembling into living organisms. This connection to cosmic history means that understanding the galaxy and our place within it reveals something profound about our own origins and nature, demonstrating that we are not separate from the cosmos but rather intrinsic parts of its long evolutionary development, matter that has become conscious through billions of years of stellar and biological evolution. The Earth that formed from this stellar debris began as a hostile, molten world bombarded by asteroids and comets in the chaotic early solar system. Gradually cooling over millions of years, our planet developed a solid crust, oceans condensed from water vapor in the atmosphere and possibly delivered by comets, and the conditions necessary for chemistry to become complex enough to cross the threshold into biology. The exact mechanism by which life originated remains one of science's great unsolved mysteries, with competing hypotheses involving deep-sea hydrothermal vents, shallow tidal pools, volcanic hot springs, or even panspermia where life arrived from elsewhere in space on meteorites. Regardless of the specific mechanism, at some point approximately 4 billion years ago, chemistry became biology, and the first self-replicating molecules appeared on Earth, beginning an evolutionary journey that would eventually lead to the spectacular diversity of life we see today. For most of Earth's history, life remained simple, limited to single-celled organisms like bacteria and archaea that gradually transformed the planet's atmosphere and surface chemistry through their metabolic activities. The oxygenation of Earth's atmosphere approximately 2.4 billion years ago, caused by cyanobacteria producing oxygen as a waste product of photosynthesis, represented one of the most dramatic transformations in planetary history, creating conditions that would eventually allow complex multicellular life to evolve. Complex multicellular organisms appeared relatively recently in Earth's history, within the last billion years, with the Cambrian explosion approximately 540 million years ago marking a dramatic diversification of animal body plans and the establishment of most major animal phyla still existing today. From that point forward, life evolved through a series of mass extinctions and subsequent radiations, with species constantly adapting to changing environmental conditions and competing with each other for resources. The dinosaurs dominated terrestrial ecosystems for over 160 million years before their sudden extinction 66 million years ago allowed mammals to diversify and eventually give rise to primates, which led to early hominids, which eventually evolved into our own species approximately 300,000 years ago. This entire evolutionary journey from chemistry to consciousness, from molecules to minds, unfolded on our small planet orbiting our ordinary star, one possible outcome of the physical and chemical laws that govern the universe operating on the material provided by ancient stellar nucleosynthesis. The rarity or commonality of this evolutionary journey remains one of the most profound open questions in science, directly impacting our assessment of our cosmic significance. If life emerges readily whenever conditions permit, and intelligence evolves commonly once life exists, then the Milky Way might teem with billions of inhabited worlds including millions hosting intelligent, technological civilizations. In this scenario, humanity represents merely one example among countless others of the universe becoming conscious of itself, making us part of a vast cosmic community even if we never make contact with other members due to the immense distances involved. Our physical smallness would be matched by our biological and intellectual ordinariness, with nothing particularly special or remarkable about Earth or humanity except to us. Conversely, if life requires an extraordinarily improbable sequence of coincidences to emerge and intelligence represents an even rarer evolutionary outcome, then inhabited worlds might be fantastically rare in the galaxy or even unique to Earth. In this scenario, despite our tiny physical scale, humanity might represent something precious beyond calculation, possibly the only consciousness in our entire galaxy or even our cosmic horizon, making our survival and flourishing a matter of cosmic importance despite occurring on a speck of dust orbiting an ordinary star. Current scientific evidence doesn't definitively resolve this question, though the discovery of thousands of exoplanets and the detection of organic molecules in interstellar space and on comets suggests that the raw materials and planetary environments potentially suitable for life might be common throughout the galaxy. The fact that life appeared on Earth relatively quickly once conditions permitted, within perhaps a few 100 million years after the planet cooled enough to maintain liquid water oceans, suggests to some researchers that the origin of life might be relatively easy given appropriate conditions. However, the fact that intelligence and technology took nearly 4 billion years to evolve on Earth, and that mass extinctions repeatedly reset the evolutionary clock, suggests that the path from simple life to technological civilization might be much more difficult and contingent on improbable events. The question remains unresolved, and both possibilities, ubiquitous life or rare life, remain consistent with current evidence. Future searches for biosignatures in exoplanet atmospheres, continued efforts to detect radio signals or other evidence of extraterrestrial intelligence, and deeper understanding of life's origin on Earth might eventually provide clearer answers. But for now, we must accept uncertainty about whether we live in a galaxy teeming with life or a galaxy where life and intelligence represent rare or unique phenomena. This uncertainty itself carries implications for how we think about our galactic context and our responsibilities as conscious beings. If we might be alone or exceptionally rare, then preserving Earth's biosphere and ensuring humanity's long-term survival takes on cosmic significance, as we might be the only observers in our galaxy capable of understanding the universe and appreciating its beauty. The loss of human civilization through nuclear war, environmental catastrophe, or other existential risks would represent not merely a human tragedy but a cosmic loss, the extinguishing of possibly the only light of consciousness in our entire region of the galaxy. This perspective motivates what some philosophers call long-termism, the view that we should prioritize the long-term flourishing of humanity and life on Earth, taking seriously our potential to either establish a lasting civilization that could persist for millions or even billions of years, or to destroy ourselves and extinguish consciousness in our corner of the cosmos. Conversely, if intelligent life proves common throughout the galaxy, then while human extinction would still be tragic for us and represent the loss of our unique culture and achievements, it wouldn't constitute a cosmic-scale loss since countless other civilizations would continue to exist and evolve, ensuring that consciousness persists in the galaxy regardless of what happens to any particular species. The practical implications of our cosmic smallness extend to how we approach space exploration and our relationship with other worlds. If humanity ever develops the capability to travel to and potentially settle other star systems, we will face profound ethical questions about our responsibilities to any life we might encounter and to the environments we enter. The history of European colonization of the Americas provides sobering lessons about what happens when technologically advanced civilizations encounter less advanced ones, with the results typically including disease, exploitation, cultural destruction, and genocide. While we hope that a species capable of interstellar travel would have matured beyond such destructive behaviors, the track record of human history suggests caution about assuming moral progress automatically accompanies technological advancement. If we find microbial life on other worlds, do we have the right to terraform those planets for human habitation even if doing so destroys native ecosystems? If we encounter intelligent but less technologically advanced civilizations, should we contact them or observe from a distance to avoid disrupting their natural development? These questions might seem premature given our current technological limitations, but thinking through such issues in advance helps clarify our values and responsibilities as a space-faring species, should we ever become one. The cosmic perspective also influences how we think about the long-term future of humanity and life on Earth. Our sun will continue burning through its hydrogen fuel for approximately another 5 billion years. But long before it exhausts its core fuel and expands into a red giant that will likely engulf Earth, it will gradually brighten and increase its energy output, making Earth too hot for liquid water oceans in perhaps 1 billion years or less. This means that if humanity or our descendants hope to survive beyond the next billion years, we will need to either leave the solar system entirely, establish habitats in the outer solar system that will remain habitable as the sun brightens, or find ways to engineer Earth's orbit or the sun's output to maintain habitable conditions. While these timescales stretch far beyond any practical planning horizon and exceed the lifespan of any species we know about, thinking about such deep futures helps put our current concerns in perspective and raises questions about whether humanity has any obligations to possible future generations separated from us by millions of years. Some philosophers argue that we should consider the welfare of all possible future humans and work to maximize their number and well-being, while others suggest that being separated from us by such vast time spans have no claim on our moral consideration, and we should focus on nearer-term concerns. The galaxy's own future evolution provides another dimension of cosmic context worth considering. Approximately 4 billion years from now, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor currently approaching us at roughly 110 kilometers per second. When galaxies collide, they don't crash together like solid objects but rather pass through each other like two swarms of bees, with individual stars almost never colliding due to the vast distances between them. However, Gravitational interactions during galactic mergers trigger bursts of star formation as gas clouds collide and collapse, reshape the involved galaxies dramatically, and eventually result in the two galaxies merging into a single larger elliptical galaxy that astronomers have playfully dubbed Milky. Our solar system will likely survive this merger physically intact, though our night sky would transform dramatically as Andromeda's stars mix with the Milky Ways and the supermassive black holes at each galaxy's center eventually merge in a spectacular event releasing tremendous gravitational wave radiation. If humanity or our descendants still exist 4 billion years hence, they will witness one of the cosmos's most dramatic spectacles as two galaxies containing perhaps 1 trillion stars total merge together over hundreds of millions of years, completely transforming the visible universe as seen from Earth, or wherever our descendants might be located by that time. Looking even further forward into the deep cosmic future, the galaxy's fate depends on the ultimate destiny of the universe itself, which remains uncertain pending better understanding of dark energy and the universe's overall geometry and content. Current evidence suggests the universe will continue expanding forever, accelerating under the influence of dark energy, eventually entering what cosmologists call the heat death scenario, where galaxies become isolated from each other as space expands between them faster than light can cross, stars exhaust their fuel supplies and die without new star formation to replace them, and the universe gradually grows cold and dark over trillions of years. In this scenario, the Milky Way or its merger product Milky will eventually exhaust all available gas for star formation, with the last generation of stars dying perhaps 10 trillion to 100 trillion years from now. After that, the galaxy will persist as a collection of stellar remnants including white dwarfs, neutron stars, and black holes, gradually cooling toward absolute zero and experiencing no significant events except the occasional collision between stellar remnants over timescales that dwarf the current age of the universe by many orders of magnitude. Eventually, even these remnants will decay through exotic processes like proton decay if it occurs, or evaporate through Hawking radiation in the case of black holes, until finally nothing remains but an almost perfectly uniform distribution of fundamental particles or energy at temperatures approaching absolute zero, achieving maximum entropy and the complete heat death of the universe. These far future scenarios, while speculative and dependent on physics we don't fully understand, provide ultimate context for our cosmic situation. Not only are we small in space, occupying a tiny fraction of the galaxy's volume and an infinitesimal fraction of the observable universe, but we also exist during a brief golden age when stars still shine and galaxies still form, long after the Big Bang but long before the heat death. Our current cosmic era, sometimes called the stelliferous era when stars dominate the universe's energy budget, began roughly 100 million years after the Big Bang when the first stars formed and will continue for perhaps 100 trillion years into the future until the last stars die, representing approximately 1% of the universe's total timeline if the heat death scenario proves correct. Humanity emerged approximately 13.8 billion years after the Big Bang, meaning we exist very early in cosmic history when measured against the full timeline, during the first fraction of 1% of the universe's total existence. This temporal context adds to our smallness, revealing that we exist not just on a tiny world but also during a brief window of cosmic time when conditions permit the existence of complex structures like stars, planets, and life. Yet this temporal smallness also carries a more hopeful implication. If we exist so early in cosmic history, then potentially the universe has barely begun its journey and vast futures stretch ahead in which consciousness and complexity might flourish in ways we cannot imagine. While individual civilizations might be brief and individual conscious beings ephemeral, the phenomenon of consciousness itself might persist throughout the stelliferous era, with new species and civilizations constantly emerging as old ones go extinct, ensuring that somewhere in the universe, awareness continues and matter continues to observe itself. In this view, humanity represents not a unique spark of consciousness in an otherwise dead universe but rather one wave in an ocean of awareness that has already existed for billions of years and might continue for trillions more. Our particular culture and civilization will certainly end eventually, whether through extinction, transformation into something we wouldn't recognize, or evolution into descendant species, but the light of consciousness we carry might be passed forward to others, either our own descendants or other species that evolve elsewhere, ensuring continuity of awareness even as particular instances come and go. The question of what we owe to this possible vast future of consciousness returns us to practical concerns about how we should live and what we should prioritize given our understanding of cosmic scale. Some argue that recognizing our smallness should inspire humility and cooperation, acknowledging that the tribal conflicts and ideological disputes that divide humans appear trivial and even absurd from cosmic perspective, like single-celled organisms fighting over territory inside a drop of water unaware of the vast ocean surrounding them. If we truly internalized our cosmic situation, perhaps we would set aside our differences and work together to address shared challenges like climate change, nuclear weapons, pandemic diseases, and other existential risks that threaten our continuation as a technological civilization. Others argue that cosmic perspective should inspire boldness and ambition rather than humility, motivating us to expand beyond Earth and establish humanity's presence throughout the solar system and eventually the galaxy, refusing to accept our current smallness as permanent, and instead working to grow our sphere of influence and understanding until we become genuinely significant on cosmic scales. Still others maintain that cosmic perspective should simply inform our worldview without necessarily dictating specific actions or priorities, providing context for our decisions without determining their content. Returning finally to the central theme with which we began, the overwhelming realization of how genuinely small we are in the Milky Way combines intellectual understanding with emotional impact in ways that few other scientific discoveries can match. Learning that Earth orbits the Sun rather than vice versa represented a major conceptual shift, but didn't fundamentally challenge human significance since we remained inhabitants of a planet at the center of a modest system. Learning that the Sun represents one star among many was more challenging but still left room for imagining humanity might be unique or special among those stars. Learning that the Milky Way contains hundreds of billions of stars and likely billions of potentially habitable planets, and that our location in this vast structure appears thoroughly unremarkable in every measurable way, completes the Copernican revolution and forces us to confront our cosmic status honestly and completely. We are small, not just in comparison to nearby objects like the Sun or nearby planets, but small when measured against the entire structure of our galaxy, occupying a volume of space that represents a rounding error in calculating galactic volume and existing for a duration that represents an eye blink in galactic time. This final synthesis of our journey outward from Earth through the solar system and beyond to our galactic context leaves us with a choice about how to interpret and respond to the knowledge we have gained. We can view our smallness as depressing and meaningless, rendering human concerns trivial and human achievements pointless when measured against cosmic scales. We can view our smallness as liberating and inspiring, freeing us from cosmic pressure and allowing us to create our own meaning and purpose without requiring universal significance. We can view our capacity to comprehend our smallness as itself significant, marking consciousness as something special regardless of the physical scale it occupies. Or we can hold multiple perspectives simultaneously, acknowledging our cosmic insignificance while still finding genuine meaning and value in our lived experience, recognizing that different scales of analysis reveal different aspects of truth about our situation. The galaxy doesn't care about our choice and will continue its slow rotation and gradual evolution completely indifferent to human interpretations of significance and meaning, but that indifference itself represents important information about our situation that we ignore at our peril. The magnitude of the Milky Way and our tiny place within it will continue to inspire wonder, dread, curiosity, and reflection as long as humans exist to contemplate their cosmic context. Each new generation will rediscover these truths and struggle to integrate them into their understanding of themselves and their place in reality. Each advance in astronomical observation will refine our measurements and potentially reveal new surprises that force further adjustments in our cosmic worldview. And through it all, we will remain inhabitants of a small rocky planet orbiting an average star in an unremarkable location within a large galaxy, simultaneously insignificant and remarkable, tiny and profound, ephemeral and potentially cosmically important. Forever small but forever reaching toward understanding the vastness that contains us and finding meaning in the very act of comprehending our own incomprehensible smallness. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.